The man bought a tie with tiny white diamonds.
Okay. A clear sartorial choice.
Right. I mean, it seems like the most, boring, straightforward sentence imaginable. A guy went to a store, purchased some neckwear, and had a little pattern on it. End of story. But, and this is why I love these deep dives, if we actually look at what your brain just did to understand that sentence,
Yeah.
it is nothing short of a computational miracle.
It really is. To you, that sentence was clear. Instantly. But to a machine or even to another part of your brain, that sentence is a minefield.
A minefield? Come on. It's a subject-verb-object sentence. Not exactly James Joyce.
Visually, sure. But let's just look at the hidden ambiguities. First of all, tie.
Right.
You assumed it was a piece of fabric you wear around your neck. But tie could be a verb like tie your shoes. It could be a sports score-a-tie game.
Okay, but context clues. The man bought a tie. You don't buy a scoreboard result.
Fair point. But then we hit diamonds. You assumed a geometric pattern on the fabric. But diamonds are also a currency.
Valuable gemstones.
Right. So grammatically, with tiny white diamonds, could describe the tie, meaning the tie has a pattern. Or it could describe the transaction. Syntactically, yeah. The man bought a tie using tiny white diamonds. As in, he slapped a handful of gems on the counter to pay for it.
Okay, that is an image. But honestly, that's ridiculous. Nobody pays for a $20 tie with loose diamonds. My brain didn't even pause to consider that.
And that is exactly the point. Why didn't you consider it? It's not grammatically illegal. It's just, well, it's statistically unlikely. And that instantaneous, invisible decision-making process, ignoring the paying with gems option because the odds are so low, is exactly what we're exploring today. We are looking at a concept called constraint satisfaction.
And we are basing this deep dive on the work of Mary Ellen McDonald and Mark Seidenberg, specifically their chapter on this. And essentially, their argument is that the brain isn't a dictionary, it's a gambler.
It's a high-speed betting machine. We are constantly playing the odds, using just massive amounts of statistical data to guess what people mean in real time.
Which, ironically, sounds a lot like how modern large language models work, predicting the next word based on probability.
It's very similar. And what we're going to see is that humans were the original statistical learning machines, long before any of this AI showed up. But this view that we are just surfing on waves of probability, that was actually a huge fight in the scientific community.
Right, because before this whole gambling theory took over in the 90s, the dominant view was much more rigid. We're talking about the two-stage model, right?
Correct. Through the 1980s, the dominant theory was modularity. The idea was that the brain is a modular machine with separate encapsulated compartments.
Like an assembly line.
Exactly. And language processing happened in a serial line, one step at a time. Stage one was the parser. This part of the brain was considered fast, automatic, and essentially dumb.
Dumb in what sense?
In the sense that it was informationally encapsulated. It didn't care about context or meaning. It just looked at the grammatical category. It sees the man bought a tie, and it applies a rule. Noun, verb, noun. It builds a syntax tree based on the laws of grammar. It doesn't care if the sentence is the man bought a cloud or the man bought a tie. It just builds the structure.
I actually kind of like that. It feels logical, like a compiler in code. You check the syntax first, then you run the program. If the syntax is wrong, don't even bother executing.
It is logical.
Yeah.
And that's why researchers like Fodor championed it. It appeals to our sense of order. Plus, we know human memory is limited, right?
Right.
We can't hold a million things in our heads at once.
Right.
So the theory was that the brain had to keep things simple. Do the grammar first. It's cheap and easy. That's stage one.
And stage two is where we actually, think.
Exactly. Stage two is the context check. Only after the structure is built do we look at the real world and ask, does this make sense?
So in the old view, you'd build the structure for the man bought a tie with diamonds, and only then would stage two step in and say, hold on.
Hold on. People usually buy ties with money, not gemstones, so let's reinterpret diamonds as a pattern.
But that seems incredibly inefficient. If I have to fully build a wrong structure, just
to tear it down a millisecond later? Yeah. Wouldn't that make conversation agonizingly slow?
It would.
And that was the crack in the foundation. In the 1990s, the evidence started shifting. We moved toward this constraint-based revolution. The new view argued that processing isn't serial, it's continuous and simultaneous.
So no more waiting around for the context check.
No waiting. The idea is that the brain uses every piece of available information, context, frequency, tone, who is speaking, what you know about the world, and it uses all of that at the very same moment to compute the meaning.
So instead of a compiler running line by line, it's like a massive parallel processor.
Precisely. Crunching everything at once. And this is where the term constraint satisfaction comes in. All these different inputs, the word choice, the grammar, the context, they're all constraints. The brain is just trying to find the one interpretation that satisfies the most constraints simultaneously.
Let's ground this, because constraints can sound a bit abstract. The source material uses the piano example, which I thought was brilliant.
Oh, yeah.
It shows how even a simple noun isn't stable.
The piano is a classic. It shows how context computes, meaning on the fly. So if I say, the man is lifting the piano, what are you picturing?
I'm picturing a heavy wooden object. I'm thinking about mass, gravity, maybe a back brace.
Right. Now, what if I say, the man is playing the piano?
Totally different. Now I'm thinking about music, keys, sound, melody. The weight of the object is completely irrelevant.
But notice the word piano is the same. In a mental dictionary view, you just look up piano and get a definition. You know, a large musical instrument with keys.
Right, a static definition.
But your brain doesn't do that. The verb lifting acts as a constraint that highlights the heavy object features. The verb playing highlights the musical features. You're literally computing a different concept of the piano based on the verb.
So meaning isn't a file we open, it's a simulation we run.
Yes. And we run these simulations incredibly fast. There was a landmark experiment by Tannenhouse back in 1995 involving eye tracking and the word rose.
Rose the flower versus rose the past tense of rise.
Exactly. They put people in front of a visual display with objects and monitored their eye movements. Now, if I say he bought a rose, that's clearly the flower.
Obviously. You can't buy a verb.
But here's the kicker. When they tracked the eyes, they found that for a tiny, tiny fraction of a second, we're talking milliseconds, the eyes would often flicker toward an object representing the action of rising.
No.
Or show confusion before settling on the flower.
Wait, really?
Yeah.
Even though buying a standing up action is nonsense, the brain still considered it for a second?
It did. It suggests that the brain initially activates all meanings associated with the sound rose, regardless of whether they make sense.
So it's a dumb activation.
Right. But then, almost instantly, the constraints, context, grammar, frequency kick in and suppress the wrong meaning.
So it's a winner-take-all cage match in the brain. Flower beats standing up because the word buying is in the sentence.
That's the mechanism. And this brings us to the architecture of how this all works. We call this connectionism.
I feel like we need to distinguish this from the AI buzzwords. We aren't talking about server farms here. This is biology.
We are, but the principles are surprisingly similar. The connectionist view says we don't have a rule book in our head. We have a network.
A web of neurons.
Exactly. Vast webs of neurons. And the connections between these neurons have weights.
Weights meaning the strength of the connection.
Right. It's all about experience. Every time you hear bought followed by tie, the connection between those two nodes gets a little stronger. It gets heavier. If you hear bought followed by clouds, that connection remains weak because, nobody buys clouds.
So we are essentially statistical sponges. We just soak up the frequency of every word combination we've ever heard.
We are. And the magic happens because these constraints work in a nonlinear way.
Okay. Nonlinear is one of those terms that gets thrown around a lot. What does it actually mean here?
It means the result isn't just a simple sum of the parts. Think of it like a tipping point. The banana analogy is probably the best way to visualize this.
Lay it on me.
Okay, imagine I'm thinking of an object and I give you 3 clues. Clue 1, it's yellow.
Okay. Could be the sun, a taxi, a lemon.
A canary.
Right. The probability is spread pretty thin.
Clue 2, it's a fruit.
Okay, that narrows it down. Lemon, banana, maybe a golden delicious apple. The taxi node is now suppressed.
Clue 3, the word starts with B.
Banana. Game over.
Right. Now look at those clues individually. Yellow is a weak constraint. Fruit is a weak constraint. Starts with B is a weak constraint. But when you satisfy all those constraints at the same time, the answer doesn't just become more likely, it explodes into certainty. The network just settles into a stable state instantly.
So it's not 1 + 1 + 1 + 3. It's 1 + 1 + 1 is the inescapable truth of the banana.
Exactly. In language, we get weak cues from grammar, weak cues from tone, weak cues from context.
Yeah.
But when they all align, the meaning locks in. You don't even realize you were betting.
But what happens when the clues don't align? Because if this system is based on betting, surely sometimes we lose the house.
We absolutely do. And When the betting machine fails, we call it a garden path sentence.
Because you get led down the garden path the wrong direction.
Exactly. The most famous example in all of psycholinguistics, this is like the stairway to heaven of linguistics, is this sentence. The horse raced past the barn, fell.
The horse raced past the barn, fell.
How did that feel?
It felt like I hit a brick wall. The horse raced past the barn. Okay, I'm with you. And then just fell. My brain just goes, error 404. It feels like there's a word missing. Like it should be the horse raced past the barn and fell.
But it's not and fell. The sentence is grammatically correct as is.
Explain. Because my brain is still rejecting it.
It failed because of the main verb versus reduced relative ambiguity. When you hear the horse raced, your brain has to make a bet. Is raced the main action?
Yeah.
Is the horse running?
Yes. Of course, horses race. That's what they do.
That's the high probability bet. But raced can also be a passive description, like the car driven by my mom. You can say, the horse raced past the barn, meaning the horse that was being raced past the barn.
Oh, okay. So the horse that was raced past the barn fell.
Exactly. But because raced is so frequently used as a main verb, and because horses are animate things that like to run, your network weights just scream main verb. You bet the house on the horse running. When you hit fell, you have a leftover verb. The structure collapses. You have to backtrack and reanalyze.
That is painful. It really shows how reliant we are on those probabilities. But the text mentions that not all of these crash the system.
Right. Compare the horse raced with this. The landmine buried in the sand exploded. The landmine buried in the sand exploded. That's easy. Structurally, it's identical. The horse raced. The landmine buried. But you didn't stumble. Why not?
Because landmines don't bury themselves.
Bingo. This is the animacy constraint. Landmines are inanimate. They can't perform the action of burying. So your brain immediately bets on the passive voice. The landmine was buried. The constraints align perfectly, so you don't garden path.
It's amazing how much knowledge about the physical world is hard-coded into our grammar processing. You have to know about the agency of landmines just to understand the syntax.
It is. We are using world knowledge to solve grammatical equations.
This brings up a really fundamental question. We've been talking about these statistics, frequency, probability. Where do they even come from? Who is writing the actuarial tables for our brains?
This is one of the most elegant parts of the theory. It's called the Production Distribution Comprehension Account, or PDC.
PDC. Sounds corporate.
It's actually very biological. The basic idea is that the statistics we use to understand language come from the way people produce language.
So we listen to how people talk and we build our stats from that.
Yes, but here is the key. Speakers are essentially lazy. Or, if we want to be polite, we're efficient. We have a production bias.
We want to get the point across with the least amount of caloric effort.
Exactly. We tend to put shorter, easier words earlier in sentences. We tend to use structures that are easiest to say. We avoid overly complex phrasing unless we absolutely have to.
So if I'm speaking, I'm not going to say the horse that was raced past the barn if I can just say the horse ran.
Right. But if you did mean the passive version, you would probably include the words that was to avoid confusing your listener to the horse that was raced. The fact that you didn't use those helper words gives the listener a statistical clue.
So as a listener, I'm sitting there thinking, okay, if he meant the passive version, he would have signaled it. He didn't signal it, so he must mean the active version.
You're reverse engineering the speaker's laziness. You are betting that the speaker is following the usual patterns of efficient speech. The distribution of language, the data set out there, is shaped by these production biases, and our comprehension tunes itself to that distribution.
That is fascinating. We aren't just decoding words, we are predicting human behavior.
However, I have to play the skeptic for a moment.
Yeah.
Not everyone buys this constraint-based view entirely.
I was going to ask, it seems very elegant, but science is always messy. What's the counter-argument?
Well, researchers like Traxler and Van Gompel have raised some interesting points. They argue that if the brain is really weighing two competing options, like flower rows versus standing rows, that competition should take effort. It should cost cognitive resources.
It should take more time to process. If I'm wrestling with two meanings, I should read slower.
Right. But some studies show that ambiguous sentences are sometimes read just as fast as unambiguous ones.
Really?
Yeah. If the competition is happening, it's surprisingly free in terms of processing time.
So there isn't always a competition cost?
Not always. And this leads to a really relatable concept called good enough processing.
Good enough. This sounds like my approach to assembling IKEA furniture.
It's very similar. The idea is that sometimes the brain doesn't actually resolve the math perfectly. We don't figure out the exact syntactic tree. We just grab a good enough interpretation to keep the conversation moving.
We skim.
We skim deeply. If I say the dog bit the man, you don't analyze the syntax. You hear dog bit man, and you assume the dog did the biting because men don't usually bite dogs. Even if the grammar was weird, like the dog bit was the man, you might still hallucinate the correct meaning.
We hallucinate meaning.
We do. We are cognitive misers. Deep processing is expensive. So if the semantic cues, like dog and bite, are strong enough, we might just ignore the syntax. We settle for a shallow understanding.
That actually explains so much about internet arguments. People aren't really reading the sentences. They're grabbing keywords and guessing the meaning.
Exactly. We coast on good enough processing until the signal fails completely, like in the horse sentence. And only then do we stop, rewind, and actually crunch the grammatical numbers.
So, to synthesize all this, we started with "the man bought a tie." We realized that understanding that simple sentence involves navigating this massive sea of probabilities. We aren't following a static rule book. We are surfing on dynamic waves of statistics, weighing animacy, context, and frequency all in milliseconds.
That's the perfect image. Ambiguity is ubiquitous. It's everywhere. But we are so incredibly good at weighing the odds that we make it look easy. We really are the ultimate betting machines.
And it really changes how I think about listening to people. I'm not just hearing them, I'm predicting them based on a lifetime of data.
And that raises a really important, perhaps slightly unsettling question to leave our listeners with.
Go for it.
If our entire understanding of language, and by extension the ideas people share with us, is based purely on the statistics of what we've heard before, are we ever truly hearing something new?
What do you mean?
Well, if we interpret ambiguous situations based on what is most common in our past experience, aren't we just reinforcing our own biases? If our brain is wired to pick the winner based on previous frequency, does that mean we are biologically wired to reinforce stereotypes and conventional wisdom?
That's heavy. You're saying our neural networks might be trapping us in an echo chamber of our own linguistic history. We hear what we expect to hear.
Exactly. Are we seeing the objective truth of the words or just the average of our past experiences?
That is going to keep me up tonight. We might just be predicting the world we already know, rather than seeing the one that's actually there.
It's a distinct probability.
Well, on that existential bombshell, we'll wrap it up. Thanks for joining us on this journey through the brain's betting machine. See you in the next deep dive.